Welcome to the deep dive. Today, we're plunging into something really at the forefront of AI and data science.
hmm
It's about how we make these super powerful deep learning models actually, work efficiently with the kind of huge, messy time series data we see everywhere.
That's right. Time series data, think stock prices, sensor readings, medical signals, it's all sequential. And often it comes in these incredibly long streams.
Right. And the models we're building now, especially things like transformers and state space models, they're amazing at finding patterns.
But they really hit a wall when you feed them these very, very long sequences. They just weren't built for that scale initially.
The computational cost just goes through the roof. Memory usage, processing time.
It's a huge bottleneck. It stops us from using the best models on many real world problems where you need to look at long histories.
Exactly. So today we're diving into a really interesting new research paper. It's called Efficient Time Series Processing for Transformers and State Space Models through Token Merging.
By Goods and colleagues. And their main idea is this technique, token merging.
Right. The goal seems pretty clear. Find a way to make these modern deep learning models way more efficient when dealing with long time series.
Speed them up, basically, without breaking the bank computationally.
And our mission here is to unpack this paper for you. We want to look at the clever ideas they came up with, explain how they work, show you the pretty impressive results.
And talk about what it all means if you're someone who works with this kind of data, or even if you're just curious about where this field is heading.
Okay, so let's start with the core problem. Why is it so computationally challenging? You mentioned transformers.
Yeah, with standard transformers, the big issue is the attention mechanism.
Ah, attention, the part that lets the model figure out what input data is important. Clever stuff, but I remember hearing it has scaling issues.
Exactly. Standard self-attention, the kind in the original transformer, scales quadratically with the sequence length.
Quadratically. So just to make that concrete, double the amount of data you put in.
And the computation for attention doesn't just double, it goes up by 4 times.
4 times the cost just for doubling the length. Wow. You can see how that gets out of hand really fast. Processing a year of data minute by minute seems tough.
It is. You hit memory limits, things slow to a crawl. It's a major hurdle when time series sequences are often thousands, maybe tens of thousands of steps long. Like the data in the Monash forecasting archive, lots of long sequences there.
Now, people have developed other models, right? Like state space models, SSMs. I heard they scale better.
They do. SSMs offer subquadratic scaling better than quadratic, often closer to linearitmic or even linear in some aspects. They're much better suited for sequences running into the millions.
But there's always a but.
Well, even SSMs, which are a big step forward, still face significant computational demands when you get to truly massive sequences. We're talking extremely long inputs.
So whether it's a transformer or an SSM, if the sequence is long enough, you still run into performance issues eventually.
Pretty much. Which leads to the idea in this paper. Can we somehow reduce the amount of data the model actually has to look at?
Enter token merging
Exactly. Token merging. The basic idea is, well, it's pretty intuitive. Find parts of the data, the tokens, that are very similar or maybe redundant.
and combine them, merge them into one.
Precisely. You create a single token to represent multiple similar ones. By doing that, you shrink the total number of tokens the model needs to process.
And fewer tokens means less computation, especially for things like attention that really depend on that sequence length.
Right. It directly attacks that scaling problem.
Okay, but this idea of merging tokens, it's not completely brand new, is it? I feel like I've seen it mentioned in other areas.
You probably have. It actually got its start, or at least gained popularity, in computer vision, particularly with vision transformers, or VSTs.
Ah, for images. How did they use it there?
They used it to handle high-resolution images more efficiently. An image can be broken down into many small patches or tokens. If some patches are very similar, like areas of blue sky, you can merge their representations.
Makes sense for images. But time series feel different. Images have space, time series have, well, time, a strict order.
That's the crucial difference. You can't just take the vision approach and slap it onto time series. The temporal order, the causality, is fundamental.
So what did this paper do differently? This is where their innovation comes in.
Exactly. This is the core contribution, adapting and refining token merging specifically for time series. And their first big idea here is what they call local merging.
Local merging. Okay, how does that differ from the global merging you might see in vision?
Good question. Global merging might look across the entire image or the entire sequence for similar tokens anywhere. Local merging, as the name suggests, introduces a constraint, locality.
Meaning,
It only calculates similarity and considers merging tokens that are close to each other within a defined local window or neighborhood. There's a parameter k that controls the size of this neighborhood.
So instead of comparing a data point now to one from last week, you might only compare it to points from the last hour or the last few steps, depending on K.
Exactly like that. It focuses on finding similarities or redundancies that are close together in time.
And this local approach, you said it has major benefits, especially academically novel ones.
Yes, two really significant ones. The first is about variable complexity.
Variable complexity. What does that mean for merging?
With global merging, even though you reduce the sequence length after merging, the process of finding those similar tokens globally still involves comparing everything to everything else, which is itself a quadratic operation.
So the merging step itself could become the bottleneck if you're not careful. Still quadratic.
Potentially, yes, but with local merging, because you only compare within that small local window defined by k, the cost of finding merge candidates drops significantly.
And if K is really small, say K equal 1, just looking at adjacent tokens.
Then the complexity of the merging process itself becomes linear with the sequence length.
Linear, that's huge. That kind of scaling is what makes SSMs attractive for long sequences.
Absolutely. Getting linear complexity for the merging step means it plays nicely with the efficiency goals of SSMs and doesn't introduce its own scaling problems when you're dealing with those ultra-long sequences. It scales properly.
Okay, variable, even linear, complexity, that's a big plus. What's the second major benefit of going local?
This one is arguably even more critical for time series forecasting, causal merging. This paper introduces the first token merging method specifically designed to maintain causality.
Causality, meaning information only flows from past to future. Why is that so essential here?
Well, think about forecasting. You're predicting the future using only past information. You can't let information from time step 100 leak back and influence your understanding of time step 10. That's cheating.
Right. Standard global merging would break that, wouldn't it? If you merge token 10 and token 100 just because they look similar.
You've just created a shortcut for information to travel backward in time that completely messes up models that have a decoder structure for generating future predictions step by step, as they rely on that strict causal flow.
So how does local merging fix this? How does it stay causal?
It mainly comes down to that small k, especially k equals 1, when you only consider merging adjacent tokens, say token I and I plus 1, and you merge them into the position of the earlier token, token I, you ensure information only moves forward by one step at most during the merge.
Okay.
The representation at time I now incorporates info up to I plus 1, but crucially, it doesn't pull in anything from further in the future. When combined with causal masking in transformers, this prevents improper information leakage.
Got it. You're only blending immediate neighbors. And what about getting the sequence length back for prediction? If you merge tokens in the middle but need to predict, say, 10 steps ahead.
They handle that with an unmerging process. It essentially reverses the merge. If one token in a layer represents two merged tokens from the layer below, the unmerging step duplicates that token's representation back into two identical tokens for the next layer.
So it restores the original length needed for the output layer.
Exactly, and it preserves causality because it's just undoing the causal merge.
Very clever. So local and causal merging are the big technical contributions. You also mentioned dynamic merging briefly.
Yes, dynamic merging is another refinement. Instead of merging a fixed percentage of tokens all the time, it decides how many tokens to merge adaptively for each specific input sequence or batch element.
How does it decide?
It uses a similarity threshold. It looks within the local windows and merges tokens only if their similarity exceeds a certain level. So some sequences might get merged more, others less, depending on their content.
So it's trying to be smarter, more tailored to the actual data passing through.
That's the idea. It could potentially give better quality results, especially maybe in situations with small batch sizes, like running models on a device where you want to optimize for each input individually.
Okay, these are fascinating techniques. Local, causal, dynamic merging, that's the theory. How did it perform in practice? Did they test this thoroughly?
Oh, yes. They did a really comprehensive evaluation. They didn't just use one model type. They tested it across 5 different transformer architectures, plus 2 major state space models, Hyena DNA and Mamba.
Different models, okay.
Different model sizes too, small to large. And they used 6 different data sets, standard forecasting benchmarks, plus some very long sequence stuff like genomic data.
Sounds robust. So what were the results? The big headlines?
The efficiency gains were, frankly, pretty dramatic in some cases.
Don't leave us hanging. Give us the
All
numbers.
right, all right. For pure speed up during inference, just running the model, they reported up to 5,400% acceleration on the Chronos Foundation model.
Wait, 5,400%?
Yes, that's a huge pre-trained time series model. And on other pre-trained transformers, they saw speedups of up to 3.80x.
5,400%. That's not just incremental. That completely changes the game for feasibility. What took an hour now takes, what, a minute?
Roughly, yeah. It means models that were just too slow or needed too much memory might suddenly become practical for real-world deployment or faster experimentation.
And crucially, you said this is during inference, so you can take a body someone else already trained.
And just apply this merging technique on top to speed it up without needing to retrain it from scratch. That's a massive practical benefit.
Does it work even if the model already uses other speedup tricks, like sparse attention?
Yes, they found it's orthogonal, meaning it can add on top of existing efficiency methods like sparse attention, potentially giving you combined benefits.
Okay, speedups are great, but you hinted earlier at something even more surprising. Sometimes accuracy actually improved. How is that possible if you're effectively throwing away data by merging tokens?
That was one of the most interesting findings. On certain data sets, they saw forecasting accuracy go up by as much as 9% when using token merging.
9% better predictions by reducing the information. That seems counterintuitive.
It really does. It challenges that simple assumption that more data, more tokens, always equals better results.
So what was going on? Did they figure out why this happened? They mentioned seeing different patterns.
They did. They basically saw three outcomes. Sometimes, as you'd expect, merging more aggressively led to a gradual drop in accuracy information loss. Other times, accuracy stayed roughly the same even with moderate merging.
And the third pattern was this unexpected improvement.
Exactly. Accuracy would initially get better as they started merging, maybe plateauing or eventually dropping if they pushed the merging too far.
Let's dive into that improvement. Why would merging help? What's the paper's explanation?
Their core hypothesis is really elegant. They propose that local merging acts like an adaptive low-pass filter.
Adaptive low-pass filter. Okay, break that down. What's a low-pass filter do, simply?
It lets the slow, smooth changes in a signal pass through, but it dampen or removes the rapid fluctuations, the high frequency stuff, which is often noise.
Like smoothing out sharp spikes or jitter in the data.
Exactly. Now think about what merging does. It finds tokens that the model thinks are similar based on their learned representations, and it averages them together. Averaging inherently smooths things out.
Ah, so the averaging process itself acts like filtering.
Precisely. It tends to reduce the high frequency components in the token representations. And because the decision of what to merge is based on the model's learned similarity at that specific point in the network for that specific input, it's doing this filtering adaptively.
Tailored to the data it's seeing right then. Did they test this filtering idea?
They did. They compared it to applying a standard non-adaptive low-pass filter, like a Gaussian filter, to the input data before it even hit the model.
And
And they found that pre-filtering also improved performance on some of the same data sets where merging helped, suggesting a similar mechanism was at play. Sometimes combining pre-filtering and token merging gave the best results. It strongly supports the idea that merging is performing this useful filtering function.
okay, so if merging acts like a noise filter, it should work best on noisy data, right? Did they connect this to the properties of the data sets themselves?
Yes, and this is another really key insight. They found that the data sets showing the biggest quality improvements from merging were the ones with higher spectral entropy or higher total harmonic distortion, THD.
Spectral entropy, DHD, those sound technical again. Can you give us the intuition?
Sure, think of spectral entropy as measuring how complex or spread out the frequencies are in your signal. Low entropy might be a simple, smooth wave. High entropy means the signal is a jumble of many different frequencies and patterns, looking complex, maybe jagged or noisy, like a busy stock chart.
Okay, high entropy equals complex, noisy-looking signal. What is THD?
Total harmonic distortion, roughly speaking, measures how much a signal deviates from a clean, fundamental pattern due to extra noise or complexity at related frequencies. High THD also generally points to a signal that's less smooth, more distorted, with more high-frequency variations relative to its main trend.
Got it. So high spectral entropy or high THD both suggest the signal is inherently more complex, maybe has more noise or rapid fluctuations.
Exactly. And the paper showed a strong link. Datasets with these characteristics, they mentioned ETF1, ETTM1, which are electricity transformer temperatures, and a traffic dataset benefited most in accuracy from token merging. The merging was effectively filtering out some of that noise or unhelpful high-frequency detail.
While datasets that were already smoother, like maybe electricity load or weather data,
Those saw less quality benefit, or sometimes a slight decrease because there was less noise to filter, and merging might have removed useful, smoother details.
that's really cool. It means you could potentially analyze your time series data first, look at its spectral properties,
And get a pretty good idea beforehand whether token merging is likely to just speed things up or if it might actually improve your model's predictive quality too.
it gives you a scientific reason for why it might work better on some data than others. Did model characteristics matter too?
They did. They found that models whose internal layers tend to learn representations where nearby tokens are already quite similar numerically, the non-stationary transformer was an example, tended to handle merging better without losing accuracy.
Because merging similar things doesn't lose much information.
Right. Whereas models where token representations stay more distinct even for nearby tokens like the Informer architecture were sometimes less robust to merging, presumably because combining distinct things lost more valuable detail.
So it's a combination, the merging technique, the data's properties, and the model's internal behavior all interact.
It's a great example of how these things connect.
And you mentioned this wasn't just for transformers, they got it working well for state space models too.
Yes, which is really important for those super long sequence applications like genomics where SSMs shine. They showed local merging worked effectively on Hyena DNA and Mamba.
And was the local aspect, especially k=1 linear merging, the key there?
Absolutely crucial. SSMs get the efficiency from avoiding quadratic costs. Using a global quadratic merging method would kill that advantage, but local merging, especially at k=1, offers a linear complexity merging process.
So it matches the efficiency profile of the SSM itself.
Exactly. It lets them add merging to get even more speed or handle even longer sequences without introducing a new bottleneck. It just fits.
This all sounds incredibly practical, not just a theoretical exercise.
No, the implications are very real world. Token merging gives us a practical tool to significantly cut the computational cost of running these very powerful time series models.
Which matters for everything from research budgets to energy consumption to deploying models on less powerful hardware. You could run bigger models like Chronos more cheaply.
Or maybe get the same performance from a smaller model, but much, much faster.
And the ability to accelerate models after they've been trained without fine-tuning is just huge for practical adoption.
Definitely lowers the barrier to entry. They also noted that if you do train with merging enabled from the start, you might get even better final results and potentially speed up the training process itself.
Adds another potential win. Okay, so let's try to wrap this up. This paper by Guts and colleagues seems like a really significant contribution. They've effectively brought token merging into the time series world.
But not just copied it, they innovated with local and causal merging, addressing the specific needs of time series data.
Unlocking these huge efficiency gains, sometimes over 5,000%, and even, quite unexpectedly, boosting accuracy in some cases.
And they gave us a compelling reason why that accuracy boost happens, the adaptive low-pass filtering effect, and showed how it connects to fundamental properties of the time series signal itself, like spectral entropy.
That connection between the signal's nature and how a deep learning technique performs feels really powerful.
It moves us towards a more principled way of applying these methods, beyond just trying things randomly.
So thinking about that connection, if analyzing basic signal properties like frequency content can predict how well something like token merging works,
Yeah.
it makes you wonder, right, for you, our listener, if understanding these fundamental characteristics of time series helps us understand filtering and merging in deep models, what other classic signal processing concepts or analyses might hold the key to designing even better, more efficient, or more interpretable deep learning architectures specifically for time series data in the future?
Are there other signal properties we should be looking at to guide model design?
It feels like there's still a lot to explore at that intersection between classic signal understanding and modern deep learning.
Definitely fertile ground.
Something to think about. That brings us to the end of this deep dive.